Hey everybody, welcome to a new video in the Generative Music AI course. In the previous lecture, we covered the theory behind Cellular Automata. Today, we're going to take that theory and implement it in a Python code. In particular, we're going to be building a drum generator that leverages a cellular automaton. Let's take a quick look at what we're going to be building with some level of detail. We're going to be building a two-dimensional automaton. In particular, on the x-axis, we're going to have time. On the y-axis, we're going to have the three drum instruments that we are going to be building, we're going to be playing around with. That is kick, snare, and hi-hat. Also, another important thing in this case is that we're going to have a binary state. So each cell can take two values, that is on or off. In the case of on, of course, we have a drum hit. In the case of off, well, it's just a rest or silence. Okay. We're going to be implementing 4 different transition rules. I've called them syncopation, resolution, filling gaps, accenting, and mutation. Of course, you'll get all the details about this once we switch to code. Finally, I just want to mention that we are going to be dealing mainly with 2 classes. The most important one, of course, is the first one called CellularAutomatonDrumGenerator. This is where all the magic happens. Then we also have a utility class that will allow us to move from the state of the cellular automaton, and that will be basically the output of the cellular automaton, and convert that into a Music21 score that then we can visualize and play back in MuseScore. Without any further ado, let's move on to code. Here we are, guys, in the CellularAutomaton.py file. Here you have the whole implementation. It's quite long. So, of course, I'm going to just walk you through the code and not implement it line by line. Let's go to the main entry point. I just want to give you a high-level overview of how all things work, and then we're going to dive deeper into the implementation details. Okay, so in the main function, we do everything, basically. So the first thing we do is we instantiate the 2 objects, the 2 classes that we saw. Basically, we instantiate the drum generator, and in order to do that, we call this constructor, and we pass a pattern length, that is the number of beats that we want to generate. Then we also instantiate a music converter, and at this point, we just run a loop, and in this loop, we run at every step DrumGenerator.step. Step is the main method of drum generator of this cellular automaton. Of course, it runs one cellular automaton update where all the rules are run at the same time. Then we want to move from the output, the state output of the cellular automaton to a Music21 score. We do that by calling the toMusic21 score method on the music converter and passing the state of the drum generator. We get a Music21 score, and now we can show that in MuseScore. I'm going to run the script for you guys so that we can also listen to one of the possible outputs of this system. Here you have the drum pattern generated with the cellular automaton. Let's listen to it. Good. Let's go back to the code and see the implementation of the different classes. First, I just want to quickly mention that in order to run the script, you have to install Music21 and NumPy. But let's get into the different classes. We have a couple of enum classes. One is DrunInstruments and the other one is DrumStates. Why do I use enum classes in this case? Well, because I don't want to deal with integers. Because, of course, I'm going to have like different indexes, like 0 for kick, or 1 for snare, or 0 for off and 1 for on in the case of drum states. But I don't want to deal directly with them. Rather, I want to have something that's more meaningful in terms of like semantic representation. And indeed, you can use this enum when you have a list of things, of constants, really, and you want to refer to them semantically. The way like this works is like this. So basically you can do something like you can have a statement like this, drum instruments dot kick, and you're basically referring to the kick, and you can also extract the value here by doing this, and this is going to be equal to 0. Okay, so here you see like the sort of how handy like this type of programming can actually be. Good. So we have drum instruments, and of course we have our 3 drum instruments, kick, snare, hi-hat, and we have drum states. And these are the states for the different cells. And you could either have off, that's equal to 0, or 1 that's equal to 1. Good. Now let's move on to the actual meat of this implementation. That is the Cellular Automaton Drum Generator. Of course, this class is where the magic happens. And let's take a look at a couple of class variables here to get started. One is called hi-hat on probability. The other one is called mutation probability. These are probabilities that we're going to be using in a couple of rules that you'll see in a while. Good. Then we have the constructor for this class. So the constructor takes an argument that is the pattern length. That's an integer that expresses the length of the drum pattern in beats. Then let's take a look at the implementation here. First, we assign pattern length to this public attribute. Then we create a new public attribute called state. This is where we actually store all the state information. That's where like we have the mathematical, the coding representation of our cellular automaton. And of course we initialize this state at the beginning, and we have a private method that does that. We'll see that in a second, but this private method takes the pattern length as an argument. Let's jump into initialize state. Let's see what this does. Well, this is just a random initialization of all the cells in the cellular automaton. Let's take a look at the implementation here. It's quite straightforward. First, we get the number of instruments, and we can get that by applying lang to the enum, drum instruments. And of course, in this case, we're going to get back 3 because we have 3 instruments. And then what we do is we actually create an array where we're going to have zeros and ones randomly distributed in all the different cells of this matrix. Because at the end of the day, this is going to be a 2-dimensional matrix. Okay. And how do we do like that random choice? Like how do we pick ones and zeros? Well, we use numpy.random.choice. Here we have the couple of options like drumstate.off.value. This is going to be a 0. This is going to be a 1. And here we suggest, we tell np.random.choice the size of the array. And this is going to be the number of instruments by the pattern length. In our case, we're going to have an array that's 3 by 16. I believe like we passed 16 beats as the pattern length in our example in the main function. Okay, so this is how you initialize the state. So we'll go back up here. Finally, we have a private attribute where we store all the rules. This is a dictionary where we basically map all the different rules like syncopation, resolution, filling gaps, so on and so forth. And we map those directly onto their private method. Why do we do this? Well, because this is going to be super handy to have clean code so that when we'll see the method that runs through all the rules, we won't have to update it every time we have a new rule, but rather like you can just add the new rule here and it's going to be way nicer. It's also like cleaner when we'll read it, and I promise it's cleaner. Good. So now let's take a look at the main function, main method for this cellular automaton class, and that is obviously step. And what it does, it advances the drum pattern by applying all the rules at the same time. Let's take a look at the implementation. We store the current state, we pass it as a new state so that we can actually manipulate this copy of the current state without altering the original state. We do this because in the rules, we're going to need to have also a reference to the current state. So we don't want to alter it while we apply the rules. And that's why we copy it and we store it here in new state. Okay, then what do we do? Well, we go through all the positions in the state. So basically we loop through all the elements until we get, let's say, the pattern length. And for each position, we apply all the rules and we get a new state back. So we have this handy apply rules method and we pass the current position and we pass the new state. And we're going to get back like a modified new state. Finally, once we've done this through all the different positions, and these are all the columns or the time steps, if you will, the moment we are done with that, we're going to assign new state to state so that we have an updated current state. Good. This is obviously a very high level implementation of this. Let's go down the stack one level and let's take a look at this apply rules method. So apply rules is quite straightforward because it applies the set of rules to the drum pattern at a given position, at a given column position, at a given time step. Okay, so let's take a look at the implementation here. We go through all the rules in the rules dictionary. So for rule in self._rules.values. So basically here we get the method, the rule method, and then we apply that. So we get this method, we pass the position, we pass the new state, and we get back a modified new state. We do this for all the rules and then we return the state. So this is when I was mentioning it's very handy to have a this private attribute, the _rules attribute, because rather than listing all the rules at once here, we can have a very nice for loop, and this is going to be way more maintainable down the line. Okay, now of course we'll have to jump into all the different rules and see what they are and how they work. So we said that we have 4 different rules. Let's take a look at the first one. So this is apply syncopation resolution rule. So the rule goes like this. If a hi-hat is on and the kick is off at a given column position, turn on the kick in the next position. Okay, let's see how we can implement this. It's quite straightforward, really. So we get the next position. So say we are at column position number 4, we get number 5, let's say. Okay, and we do this by leveraging this, calling this private method, get next position. Yeah, I just want to go through all this method first, and then we're going to take a look at this implementation. We want to check whether the cell of the hi-hat in the current position is on and the cell of the kick in the current position is off. If that is true, then what we're going to be doing is we are going to actually put the subsequent cell, the cell in the next time position for the kick to on. We're going to switch it to on. Okay. This is actually more difficult to say than to actually see how it works, because it's quite straightforward. It's just a very simple conditional. Okay, so I promised I would look into this get next position before we move on to another rule. So let's take a look at how this works. So here we just determine the next position in a circular sequence. And of course, we have to think that this is a circular sequence because the moment we arrive at the end of the sequence, we are at the last beat, if you will. We just want to wrap back at the beginning of the sequence in a circular manner. So how do we do this? Well, it's quite straightforward. We return the current index position plus 1, and we just use this modulo using the pattern length, and this will allow us to wrap back at the beginning of the sequence. Okay, we have a sort of sister method here to get next position. That is, I believe it's somewhere down here, get previous position. And let's take a look at what this is. Well, this one determines the previous position again in a circular sequence. And how does this work? So if the position is greater than 0, the index is greater than 0, then we just return the current index, position index minus 1. But if the position index is equal to 0, it means that we are at the beginning of the sequence, so we have to go all the way back to the end of the sequence and return the last index of the sequence. And we do that by doing a pattern length minus 1. Okay, this is a very nice way of dealing with circular sequences. Okay, so we now saw that we have a couple of utility methods to get the previous and the next position. So obviously this will be applied in the next rule that we're going to be checking, and that is apply filling gaps rule. Again, let's take a look at the rule. It works like this. If a kick is off in 2 consecutive positions, turn on the snare in the next position. Similarly, if a snare is off in 2 consecutive positions, turn on the kick in the next position. Okay, so how does this work? Well, we get the previous position and next position, obviously, because we are going to be dealing with 3 positions here. So the current position, the previous one, and the next one that we're going to affect. And then we have this conditional. If this is true, then we're going to do something. I'm not going to go through this because it's basically like what we said here. So let me just like repeat it here because probably it's easier than reading the code. If a kick is off in 2 consecutive positions, turn on the snare in the next position. Okay, so that's the conditional. If that's the case, then we get the cell for the next position of the snare and we turn the drum states to on. Right, and then we do something similar here. And if I remember correctly, this is if the snare is off in the previous position and in the current position, then what we do is we take the kick in the next position and we turn that to on. We're basically filling gaps here. Okay, and finally, we just return the state. Okay, we saw this private method here, so we'll move on to the third rule, that's apply accenting rule. And this one goes like this. If both kick and snare are on at a position, we turn on the hi-hat at the same position with a probability determined by hi-hat on probability. And if you remember, this was this class variable that we had up here. Okay, so we go down here and we'll take a look at the implementation. So here we check whether the kick at the current position is on and the snare at the current position is on. If that's true, what we'll do is we generate a random continuous number between 0 and 1. If that is less than the hi-hat on probability, then the new hi-hat state will be on, otherwise it will be off. Of course, once we're done with these conditional statements, we assign the new value for the hi-hat at the current position, and that's it. So that's the rule. Okay, let's move on to the final rule, that is apply mutation rule. This one applies a mutation to a random instrument at a given position, and it works like this. So for each position, we have a small probability of randomly toggling the state of one of the instruments. The instrument will be chosen randomly. And the probability of applying this mutation is given by the mutation probability. That's the class variable that we saw at the beginning of this implementation. Let's take a look at the code. We generate a random number that's a continuous number between 0 and 1. If that is less than the mutation probability, we are going to be applying the mutation rule. What this implies is first to choose an instrument, then we're going to get the cell associated to the chosen instrument at the current position, and we're going to basically flip a coin and decide whether this cell is going to be on or off. But I don't like this implementation because it's too verbose. So I'm going to just rewrite it like this. New instrument state. I'm going to pass this one here, and I'm going to get this one like this. Okay, so we get the new instrument state, and then we assign it to the chosen instrument at the current position. Good. We are done with the implementation of this quite long class called CellularAutomatonDrumGenerator. Then what remains is the other class, but that's a utility class, so I'm not gonna get into the implementation details here. If you want to do it, and you should definitely do it, just go check the code on GitHub. Let me just give you a little bit of an overview of this class. It's called Drum Pattern Music21 Converter. Of course, it converts drum patterns generated with the cellular automaton that we've just seen, and it converts them into Music21 scores. Okay, so we have one main public method called toMusic21 score. Let's super quickly take a look at how this method works. We instantiate a Music21 score, we give it a title, then we extract the pattern length, and we loop through all the drum instruments in the enum. And here we're going to loop 3 times, one for snare, one for kick, and one for a hi-hat. And for each of these, we are going to generate a Music21 part. And in the Music21 part, we're going to put all the Music21 objects and notes. Once we're done with the part, we're going to append this part to the score. Of course, we generate that part with this auxiliary method called instrument to Music21 parts. And if you want, you can just like dive deeper here and see how this works. Let's just recap everything in the main function so that you'll have once again an overview of how all of this works and it's put together, but now with a lot of awareness about the implementation details. So first of all, we instantiate a drum generator with this constructor passing the pattern length, in this case 16 beats. We instantiate an object, and that is the drum pattern Music21 converter. And then we run different steps of the cellular automaton. In this case, we run 8 steps, calling DrumGenerator.step. At this point, we have the actual drum pattern stored in DrumGenerator.state, and we have to pass this array to MusicConverter.toMusic21 score, so that we're going to get a Music21 score that then we can show. Here you have it, the Python implementation of a cellular automaton that generates drum patterns. In the next lecture, we're going to be looking at another popular technique to generate music, that is genetic algorithms. If you've liked this video, remember to leave a like, and if you're not a subscriber of the Sound of AI channel, please subscribe. It costs you nothing, and it's super helpful for me and for the growth of the channel. That's all for today. I'll see you next time. Bye for now.